So this is the 31st lecture and I'll deal with some numericals based on the topic that we discussed in the last lecture, that is the mass action law. We discussed that in mass action law the electron concentration and hole concentration is a constant and it is equal to Ni square. First of this relation we studied in the last lecture, and also we discussed the charge densities in semiconductor. For n type, I discussed that for n type where electrons are in majority, so the number of electrons in n type semiconductor is approximately equal to the donor concentration, and the number of holes P in n type semiconductor is approximately equal to Ni square upon Nd. That is, the majority charge carriers are approximately equal to the donor concentration and minority charge carriers is equal to Ni square upon Nd. And for P type semiconductor, that is, in this case holes will be majority charge carriers, so I can say that the holes in P type semiconductor is approximately equal to the acceptor concentration. What I am writing in suffix that represents the type of semiconductor, whether n type or P type. So the holes in P type semiconductor is approximately equal to the acceptor concentration, and the electrons in P type semiconductor is approximately equal to Ni square upon Na, where Na is the acceptor concentration. And of course in intrinsic semiconductor the number of electrons per unit volume is equal to the number of holes per unit volume. So let's do some numericals based on it. First numerical that I'll discuss here, just see. The first numerical is this. It says there's a problem. There's a problem here. In a doped semiconductor there are 4.52 into 10 to the power 24 holes. So if you see that the number of holes P, I represent this number of holes, is 4.52 into 10 to the power 24. This much holes per meter cube, and 1.25 into 10 to the power 14 electrons per meter cube. So the number of electrons or the electron concentration is 1.25 into 10 to the power 14 per meter cube in a doped semiconductor. It says it is in a doped semiconductor, means it's an extrinsic semiconductor. Now observe one more thing. If you observe here, you observe that looking into this data here, very first thing to understand, you have to extract certain things from this data. If you observe that the number of holes are greater than the number of electrons here, holes are greater than the number of electrons, so it is very clear that this type of semiconductor, this doped semiconductor, is a P type semiconductor. So the problem is for a P type. Doped semiconductor means it's a P type semiconductor. So I can say that these are the number of holes in P type and these are the number of electrons in P type semiconductor. Now what will be the carrier density of undoped specimen? Undoped specimen means it was doped, an intrinsic semiconductor was doped. It is asked the intrinsic concentration, density of undoped semiconductor. Undoped means when it was not doped. It is made P type after doping. So what I need is Ni. First part is Ni is asked. So I know by mass action law, since N into P is equal to Ni square, it is applicable for any type of semiconductor, whether it is intrinsic or extrinsic. So I can say this, that is the number of electrons in P type semiconductor and number of holes in P type semiconductor per unit volume is equal to Ni square. Or from here I can say that this implies that value of Ni is equal to under root of this N in P type semiconductor into holes in P type semiconductor, and I simply substitute the value of this. So I'll get the value of Ni from here will be equal to under root of value of Np is 1.25 into 10 to the power 14 multiplied by 4.52 into 10 to the power 24. And if you solve this, it is approximately equal to 2.38 into 10 to the power 19 per meter cube. That is, these are the number of electrons or holes which are equal in intrinsic semiconductor if initially when it was an intrinsic one. Now, next part, it says, look at the second part, if the electron and hole mobilities are this much, that is, this is mu n, I am writing here only, electron and hole mobilities, that is mu n is equal to this much, and hole mobility is this is mu p. Determine the conductivity of intrinsic and doped semiconductor. That is, you need the conductivity of intrinsic semiconductor and doped semiconductor, means p-type semiconductor. So first I'll find the conductivity of intrinsic semiconductor. Second part I'm interested in conductivity of intrinsic semiconductor, and this conductivity of intrinsic semiconductor is given by Ni into mu n plus mu p into the electronic charge E. And from here I can say that the value of Ni you have just calculated is just 2.38 into 10 to the power 19 into mu n 0.38 and mu p is 0.18. 0.38 plus 0.18, this much, into electronic charge is 1.6 into 10 to the power minus 19 coulomb. 10 to the power minus this 19 I have written here. And if you calculate this, please cross check this answer. From my calculation, it is approximately equal to 2.14 per ohm per meter, or I can say mho per meter. Either you say it is per ohm per meter or mho per meter. This is the conductivity of intrinsic semiconductor. Next it says determine the conductivity of doped semiconductor. Doped means it is p-type semiconductor, and I know that the conductivity of a p-type semiconductor, although it is an approximation, or okay, I'll make equal to. First of all, in general, for any semiconductor it is equal to n mu n plus p mu p, n mu n plus p mu p into the electronic charge E. This is the exact one, and you simply substitute the value of this is n mu n for mu p. This is for p type, that is the number of electrons in this much and number of holes in p type semiconductor, that is already given to you. You substitute the value n mu n plus p mu p, mu n and mu p is given to you. You can find the exact value of this. And or approximation I can do, you'll get approximately the same result. Approximation will be holes are majority charge carriers and electrons are minority charge carriers. So I neglect these from here, and these holes are approximately equal to the acceptor concentration. So I can say that this is approximately equal to the concentration of holes, that is, it is approximately equal to P holes in p-type semiconductor into mu p into E, and you simply substitute the value 4.52 into 10 to the power 24. Mu p is given to you 0.18 into electronic charge is 1.6 into 10 to the power minus 19. And you solve this. I want you to do this calculation on your own, that what is the conductivity in per ohm per meter. You will obtain it from here. I hope that this numerical is clear to you. Very first thing is to understand the numerical. From here you concluded that this is a p-type semiconductor. Very first thing is that you obtained that there is a p-type semiconductor, and from this I found the conductivity, approximate conductivity of a p-type semiconductor, although you can find the exact one also. So I hope that this is clear to you. Let's move to next problem. The next problem says that a sample of germanium, here it is, next problem, a sample of germanium is made p-type by adding acceptor atoms at a rate of 1 atom per 4 into 10 to the power 8 germanium atoms. Now try to understand this, what this problem is. It says that you have a pure germanium here. You have a pure germanium. And you add some acceptor impurity here. You add acceptor impurity to this. Okay, suppose I say its concentration is Na. The resulting is a p-type semiconductor. The resulting semiconductor is a p-type semiconductor. Of course, it is germanium. Now, what it says, look at the problem again. A sample of germanium is made p-type by adding acceptor atoms. It is made by adding acceptor atom, Na. By adding acceptor atom here. At a rate of 1 atom per 10 to the power 80 per 10 to the power 8 germanium atoms. That is what it is trying to say, that if these are the germanium atoms and this is the acceptor concentration, 1 atom per 10 to the power 8 germanium atoms in 4 into 10 to the power 8 germanium atoms. 1 atom, these are germanium atoms and these are the acceptor atoms. In 4 into 10 to the power 8 germanium atoms, 1 atom of acceptor impurity is added. This is what it wants to say, that when there are 4 into 10 to the power 8 germanium atoms, 4 into 10 to the power germanium atoms, you add 1 atom of acceptor impurity. This is what it says. Now, determine the electron and hole concentration. Determine the electron and hole concentration. So it is asked to find the value of electron concentration and hole concentration. Of course, it will be a p-type semiconductor. Since acceptor impurities, it is acceptor atoms. Just try to understand. Acceptor atom means it is p-type. So determine the value of electron and hole concentration in the doped semiconductor if Ni is equal to this much. And one more thing it is given, if the density of germanium atom is 4.4 into 10 to the power 28, density of germanium is 4.4 into 10 to the power 28. Now in this much germanium atom, 1 acceptor atom is added, so total density is this much. So since I can say that in this much germanium atom there is 1 acceptor atom, the density of this, so therefore in 4.4 into 10 to the power 28 germanium atoms, the acceptor atoms will be 1 upon 4 into 10 to the power 8 into 4.4 into 10 to the power 28. Simple unitary method. 1 atom is added in this much germanium atom, and given that the density of germanium atoms is this much, so how much Na is there? So from here I will get the value of Na, acceptor atoms. Value of Na will be, this will cancel, 1.1 and 20. It will be 1.1 into 10 to the power 20 atoms per meter cube. It means this is the acceptor concentration that has been added. This is Na, this is the quantity of Na or the density of Na that has been added to this germanium in order to make this p-type. I hope that this problem is clear to you. Now it says determine the electron and hole concentration. This is, I obtained this. At the same time, Ni is given to you 2.5 into 10 to the power 19 per meter cube, and it says that determine the electron and hole concentration. What you have to find is the electron and hole concentration. Of course, it is a p-type semiconductor because acceptor impurity is added. So it is asked to find the electron and hole concentration in this p-type semiconductor. Now I know since it is a p-type, so the holes in a p-type semiconductor is approximately equal to Na. Therefore, I can say that the holes, determine the electron and hole concentration. So the hole concentration in this is approximately equal to 1.1 into 10 to the power 28 per meter cube. This is my first answer. And whole concentration, this is the whole concentration, electron concentration, that is the minority charge carriers in a p-type semiconductor, it is approximately equal to Ni square upon Na, Ni square upon Na. So it is equal to Ni square upon Na. This Ni is given to you 2.5 into 10 to the power 19 whole square upon Na is, it won't be 28, I think it should be 20. I'm sorry, 28 minus 8, it is 20, so this will be 20. Upon value of Na, you have found it is equal to 1.1 into 10 to the power 20. So whatever you find it, this much meter cube is the final answer. Similarly, if conductivity would have been asked and mobility is given, you would have found the conductivity of intrinsic semiconductor as well as for the doped semiconductor. I hope that this problem is clear to you. That how it is by doping. Amount of doping was given to you, and from that doping was not directly given, but indirectly it was given that what is the ratio in which the acceptor impurity is added in terms of these pure germanium atoms. So I hope this is clear to you. Let's move to one more problem. I'll take this as a last problem. A bar of pure silicon has cross-sectional area. What is given to you? I am writing here. Has cross-sectional area A is 1 millimeter square. 1 millimeter square. I can say it is 1 into 10 to the power minus 6 meter square. Let's make it in this way. If the intrinsic, it is a pure silicon first of all. Just see, pure intrinsic one. If the intrinsic concentration, that is Ni, if the intrinsic concentration is 1.5 into 10 to the power 16 per meter cube, determine the first part, determine the conductivity. Oh, okay, you have to find the conductivity of intrinsic semiconductor. If the electron and hole mobilities are this much, electron mobility is this, mu n is this much, and this is mu p. I am writing here only. What is given to you that this is mu n, this value is mu n, and this value is mu p. So given that this is mu n and this is mu p, so first part is this, determine the intrinsic concentration. If the intrinsic, determine the conductivity. So you need the conductivity first part. Look at the solution of this first part. The conductivity of intrinsic semiconductor, I know it is equal to Ni into mu n plus mu p into electronic charge E, and I can say that this Ni is given to me 1.5 into 10 to the power 16 per meter cube. Mu n is 0.13 plus mu p is 0.05 and electronic charge is 1.6. This value of E is 1.6 10 to the power minus 19. If I solve this, I have done the calculation, it is 4.32 into 10 to the power minus 4. This much mho per meter or per ohm per meter, you can say. This is what I obtained. You can please cross check these results. There might be a chances of mistake here. Second part of the problem, what it says. So first part is done. Find the length of bar. It says find the length of this bar whose area is this much. You have to find the length of the bar. That is your next part is to find the length of this bar, of this bar of pure silicon, of length of this silicon bar. If its resistance is, one more thing is given to you, that given resistance is given to you, it is 50 kilo ohm. 50 kilo ohm, that is, I can say it is 50 into 10 to the power 3 ohm, and you have to find the length of this. Now conductivity I have found. If you remember, this R resistance is given by rho L upon A. So from here I can say that rho is equal to RA upon L, or from here I can say that conductivity is L upon RA. So I apply this conductivity which I have calculated, that is this conductivity, since conductivity is equal to L upon RA. I have to find this L here. This L is required. So this implies that I can find that this L is equal to sigma conductivity. Of course, this I have calculated from here. This is the conductivity into R into A. So conductivity I have just calculated. I can find that the value of L is equal to 4.32 into 10 to the power minus 4 into R 50 into 10 to the power 3, and area is 1 into 10 to the power minus 6. 1 into 10 to the power minus, it is 10 to the power minus 6. And if I calculate this, as per my calculation, this comes out to be approximately 21.6 micrometer. That is 21.6 into 10 to the power minus 6 meter. So this is what I obtain here. So I hope that to these 2-3 numericals would have made some theory clear to you that I have done in the previous lectures. I'll continue with some other topic in the next lecture. So thanks for the time being.